Welcome to the viewers. Today we discuss the topics of Laplace transform of few important functions. And for this reason, we recall the basic standard result of the Laplace transform, which we proved in earlier classes. These results are Laplace transform of t to the power n is equal to n factorial by p to the power n plus 1, and another one is shifting theorem. And the statement of this theorem, just in a nutshell, a brief statement we give: with Laplace transform of some function gt, if it exists and it will be gt for real p greater than some alpha, say some constant, then for any complex parameter lambda, Laplace transform of e to the power minus lambda t gt, that will be equals to g of lambda plus p. Already we proved this theorem in earlier classes, in earlier videos, but now with the help of these two we evaluate some of the important Laplace transform of functions. First of all, if let, for example 1, if we consider a function gt equals to t to the power n e to the power lambda t, what happens there? Then Laplace transform of gt, it will be Laplace transform of t to the power n e to the power lambda t, and we know Laplace transform of t to the power n will be n factorial by p to the power n plus 1. But here we observe here another extra term, e to the power lambda t, but we use this type of theorem: Laplace transform of e to the power minus lambda t gt equals to g of lambda plus p. So with this help of these two theorems we obtain here n factorial will be the common, but here only change occur, that is g of lambda plus p, but here only change is there. So here it will be minus lambda, so if we are taking here only lambda, so it will be minus of minus lambda, that's why lambda will be negative, that means p minus lambda terms. So here it will be p minus lambda whole to the power n plus 1. This will be the answer. It is done by shifting theorem. This theorem is called shifting theorem. So very shortly we can do, and we can evaluate these categorical functions and the Laplace transform of these categorical functions. Now we take another kind of example. If gt will be sine of alpha t e to the power lambda t, if we take these situations, what happens there if we notice? So L of gt, similarly Laplace transform L of sine of alpha t to the power lambda t. So here we generally know sine of alpha t, Laplace transform of sine of alpha t will be alpha by p square plus alpha square, and one more extra term is here, that is e to the power lambda t. So clearly we use another time shifting theorems, so it will be already taking that minus of minus lambda, that is plus lambda. Similarly here also plus lambda we observe, so here it will be minus. So using another kind of shifting theorem, what happens there? The answer will be general sign Laplace. Generally we know that alpha by This is a Laplace transform of sin alpha t, alpha by p minus lambda square plus alpha square, because generally sin Laplace transform of sin alpha t will be alpha by p square plus alpha square. So here using the shifting theorem only on p, that will be p minus lambda, no other changes is there. And similarly with shifting theorem. Now if we consider another example, Laplace transform of cos of alpha t e to the power lambda t. Similarly what happens there? So here we know Laplace transform of cos of alpha t will be p by p square plus alpha square. So here only change on p, so it will be p minus alpha by p minus alpha square plus alpha square. This will be the answer. Here you also use the shifting theorem. So in this way we can evaluate this categorical function very easily and in the shortest way. Thank you.